Hey folks, it's Michael with the Reason RX podcast. Hope you are doing well. Surviving and thriving in the midst of all this stuff we have going on in 2020. Make the best of it. Still make yourself the best you can be. Optimal cognitive and physical function, fitness function. Don't let it sap your energy or sap your life. But today, we're going to talk about engineering, the profession of engineering, thinking skills involved, educating for it, things like that. And we're talking with the engineer Hannes Hacker about this. Hannes, hello. Could you say hi to folks and introduce yourself, please?
Hello, my name is Hannes Hacker. I have just under 30 years of experience as an engineer. Engineering tends to get very specialized, and my specialty is satellite engineering and operations,
Cool.
particularly flight dynamics, attitude control, mission operations, mission systems engineering, as it's called.
And that's 30 years with a 3-0, right? 10 times
3
3.
0, yeah.
Yeah.
Yes, I've worked a little bit on the Space Shuttle program, the International Space Station, the Iridium communications constellation, various geostationary satellite programs. After that, I worked on a micro and satellite program for the Department of Defense. Moved from there to, I also worked on, it's a small space plane called Dream Chaser. A miniature space shuttle, if you will, that is, and I go into a lot more. But I currently work for a company called Globalstar, which is another communications, what they call a big LEO constellation. We have a total of, I believe, 36 satellites in low orbit for basically cellular communication and data in remote areas.
That's a lot of experience. It's like hard to retain all that.
Oh.
But cool.
So,
What about education? Bachelor's, PhD.
I have a bachelor of science in aerospace engineering from the University of Notre Dame, and a master of science in aerospace engineering from the University of Texas at Austin.
Cool.
So,
Hook 'em.
what's that? Hook 'em, yeah.
Hook 'em horns. Yeah.
And my specialty as my master's was basically orbital dynamics. I did a thesis on the atmospheric drag perturbation of satellites in low Earth orbit.
Cool. Wow.
So,
What about high school? Just average public high school or what?
well, I went to 2 high schools because my father was in the Army. So my first 2 years in high school was a high school called Ayer High School, Ayer, in Massachusetts. And it was a pretty not very good high school, I don't think. And fortunately for me, we transferred to South Bend, Indiana, where I went to John Adams High School in South Bend, Indiana, which was a significantly better high school. For example, the high school in Massachusetts would not allow me to have taken calculus as a senior. And the one and they didn't have enough teachers to teach advanced placement or honors classes in everything. So, and the new high school did, in fact, for example, their biology department was excellent. You had students at the new high school who would take 4 years of biology, and by the end they were doing research, independent research.
Wow, sweet, nice.
It was a very good school to go to, much better school to go to.
Cool.
So,
Cool. So, any other background info or interesting stories on school or college or work?
I think we can save that for a little later. When
Okay, cool.
you have some later questions about, what I think could be improved in engineering education, or at least my engineering education.
Mm-hmm. Cool. All right. So, what is engineering? How would you define that and describe it and give some examples?
Yeah, I would describe engineering as basically being an inventor or a maker. Scientists' job is to try to determine the nature of reality. And the engineer comes along and uses that knowledge to turn it into some kind of a system or product, what have you. And it can be anything, and it can be software. It can be just algorithms in a computer. It can be something as complex as an airplane, an airliner, or a satellite. Or in my case, I don't really design the satellites. I learn how they work, and my job is to figure out how to fly them, how to create it's usually software to have a satellite or a spacecraft do certain things. They do not just fly around in their orbit. There's certain maintenance things that have to be done. I'll give you an example. We did this at work today, me and a colleague. We had one of our satellites have to do a maneuver to avoid a collision with another object in space. And so there's software that me and my team have written to analyze certain things. I don't want to get into too much gory detail, but for example, there is a potential that when we slew the satellite to the direction it's pointing in space, that one of the Earth sensors, we have horizon sensors that tell the satellite what its attitude is relative to the Earth. And in this case, roll and pitch. And those are technical terms. Roll is if you think of an airplane. The satellite is, roll is if you're flying along and the wings go up and down, rolling around the direction of flight. Pitch is nose up and down, and then yaw is left and right. But when we're slewing to the attitude we need to go to, there's a potential that the sun could come during the slew, that the sun can actually enter one of these Earth sensors. And the onboard software does not know that the sun is in, during a slew, does not know that the sun is there. And so it starts feeding bad data to the flight computer. And the flight computer starts trying to correct an attitude that's already correct. And it loses the Earth, and then it goes into what we call safe mode. And that's bad because it's now no longer generating revenue. Executive management gets grumpy about that, and it's usually about at least 8 hours to get it back into service. I hope that's a good example.
And so you got to be in a certain orbit, avoid some space debris or whatever, and then get back into the same orbit?
It's not the orbit. You do. That is correct. Because what you'll do is you'll change your orbit slightly, and we've got a little, basically a box, we call it in space, that we try to stay in. Well, if you raise your orbit slightly, you're actually slowing down, and then you're going to fly out of the back of that box. So then at some point you have to turn the satellite around to lower the orbit again to stay within the box.
Mm-hmm. But what about the debris for future orbits? Is the debris usually gone after the one orbit, or what's the deal?
Not always, no. It depends on basically the worst thing that can happen is you can have an accident. You can have an actual collision. Mm-hmm. And then you've created, instead of having a single piece of debris, you've got hundreds or even thousands of pieces of debris.
Mm-hmm. And no more satellite.
Well, and there have been there have been collisions in space. The first one, I wrote a paper about this actually, was in 2007. And this was the Chinese, if you remember, in 2007, early in 2007, just as a saber rattling exercise, they intentionally destroyed one of their own weather satellites using what's called a kinetic kill vehicle. It's basically a solid chunk of metal that they deliberately collided with one of their own satellites. And they generated thousands of pieces, actually tens of thousands of pieces of debris that are now wrapped all around the Earth. The altitude was high enough that the engineering estimate is that 85% of these thousands of debris pieces will still be in orbit 100 years from now. And so now you have all of these small little debris pieces that will slowly, over a period of decades or longer, even though they're at about 780 kilometers up, there is enough atmosphere there that high up that it will, over enough time, decay the orbits and eventually have them fall back to Earth. But as they do so, there is, they are basically a navigation hazard for everything that is at that altitude and below. And they've really jumped up a very important altitude, which is around the altitude of about 800-ish, 750 to 800 kilometers, because that's where weather satellites, scientific Earth sensing satellites, military observation satellites all tend to live. And now you've got thousands upon thousands of junk pieces that nobody can control that are going to be there for decades.
And they're really hard to track. Are they pretty much all identified and they can track them, or are they kind of hard to track, or what?
It depends on the size of the debris piece. Mm-hmm. Anything about the size of a baseball or larger can be tracked. Anything between the size of a baseball and about a marble can't be tracked. It can be statistically, it's just too small to track it. You don't get a good radar return. Mm-hmm. But you can get an idea of the numbers. And and anything smaller than a marble is typically considered small enough it's not going to completely destroy a spacecraft. Mm-hmm. But that marble size to baseball size, those are the ones that are worrisome. The most worrisome.
And so there's still stuff that we can still use between 750 and 800, but it's very compromised and limited now.
It's compromised, I think, is the best word. And if you look at, and there was another accidental collision that happened, I think, 2 years later between an Iridium satellite and a Russian Cosmos satellite that happened at a very similar altitude. And if you look at a chart of the number of debris pieces on the vertical axis versus the altitude on the horizontal axis, at about 750 to 800, you get this massive spike that wasn't there before 2007. And the nickname for that is the junk belt.
And the Chinese did it on purpose?
The Chinese did this on purpose.
What did they benefit?
And they did this what's that?
What do they benefit from it? Why'd they do it?
Saber rattling, basically. Yeah. Hey, look at us. We can destroy a satellite if we want to. And they've been doing some other provocative things over the years too. But
doesn't seem like it's in their own self-interest because it affects them too.
Yes, it does.
It's nice you can destroy stuff, but it's like, hey, look, I can pollute this river, so, wait, neither of us have water to drink now, but look what I can do. I can pollute it.
Yep, exactly. The thing is, they did this very shortly before a conference that was supposed to happen in Beijing on orbital debris mitigation. So,
Hmm. Some people. Anyway, cool. Well, yeah. Um, and so, let's see. So the Romans did a lot of engineering. Greeks did a lot of the science it was based on. Um, or people learned about basic function of electricity, basic nature of electricity, and then engineers would take that and make a computer. So that's another example.
that's another example, starting with even something as simple as a light bulb to an integrated circuit to a computer. Exactly.
Or Benjamin
And
Franklin might function as both a scientist and an engineer.
yes,
Yeah. So, for
yes,
example, he did one experiment where he got pieces, like square, rectangular pieces of cloth of different color, put them out in the snow, and then he saw that there was this um, gradiated depth that they'd sink to. The darker the color, the deeper it would sink. Um, and I think that's
I didn't.
yeah, it's interesting. I'll have to make a note, maybe put that in the show notes for people. Franklin cloth experiment. Maybe that'll be enough to remind me. And what? Um, which do you remember the so-called laws of induction? Um, difference, agreement. Um, damn, I forgot the name of that one. It's in my brain. I'm just like, I guess, a little too tired to think. Mill's methods: agreement, difference, combined method of agreement, difference. Oh, concomitant variation. So yeah, so the Franklin thing they call concomitant variation. Um, but
Okay.
I think he used that to. Um, that might have been some of the basis for inventing the Franklin stove, making it dark so it absorbed
I see.
and radiated heat more. Um, and then, people weren't stupid. They already knew about light clothes and dark clothes from experience, but I think that helped give some theoretical foundation as to why people should wear certain clothes in certain environments also. Um, darker when you want to retain heat, lighter when you want to not absorb heat as much. Um, and then,
Yeah,
so he'd function as a scientist in doing the experiment, and then an engineer with the stove or the clothes or whatever. Is that right?
yes, that's a good example.
And then he did his famous kite experiment for electricity. So scientifically, we're generalizing through an experiment. All lightning is electricity, scientific, but then the lightning rod would be engineering. Is that right?
Yes,
Cool. Um,
yes. I think he grasped the idea. The way the lightning rod works is you've got basically an electrical charge that is accumulating both in the clouds and on the ground. And if that electrical charge becomes powerful enough, then you get basically a spark, except it's a very, very, very dangerous spark.
mm-hmm.
But that's what lightning is. It's the same thing as when you shuffle your feet on the floor and you touch the doorknob and you get a little spark that shocks your finger, just on a much more destructive magnitude. And he discovered the fact, and he worked out that if you take a lightning rod, the way the lightning rod works is it basically allows the charge to all get accumulated into a small area, and then just basically it blows in the wind, for lack of a better way of putting it.
Mm-hmm.
And so it doesn't accumulate on the ground; it just it gets dispersed.
Cool.
Now that doesn't stop lightning from hitting something nearby that doesn't have a lightning rod, but essentially that's how it works.
Then he also did some other similar experiments. It wasn't the kite out of nowhere, out of context, but some experiments on how sharp points attract lightning. I mean, I think the context for that, some cognitive context, was knowing that how static electricity was affected by sharp points. Um, I forget some of the other experiments he did, but yeah, there was more than just the kite experiment, and um, some of this stuff coming up, allowing him to do other inventions, also do other engineering. So cool, interesting. Any other examples you might want to mention, or you might have thought of?
Somebody who is both scientist and engineer.
Or else just engineering. The science, maybe someone who did science, and engineering someone else did.
Yeah, I mean, almost all of the science that went into the first airplane that the Wright brothers flew had already been done. And a lot of the engineering obstacles had already been done. But the main achievement of the Wright brothers, there's a couple. And you had a question here, examples of good and bad engineering. This is an example of good engineering and why the Wright brothers were so good. They started with observing reality and learning from it. For example, everybody who was trying to learn how to fly in the late 19th, early 20th century thought that you would turn an airplane into the air like you would steer a boat using your rudder. The Wright brothers figured out by observing birds that birds don't turn that way. I was talking about roll. If a bird wanted to turn in one direction or the other, they would roll into the direction that they want to turn. And so the lift, part of the lift that it is generating to keep them aloft, is now turned into the direction they want to turn. And it's that lift, it's vector math, right? It's that lift that then turns.
What's a vector for folks? Just for some folks who.
A vector is basically a three-dimensional number relative to some point, to some origin. So if you think of a bird flying along or an airplane flying along, and you have the center of gravity and it's generating lift. I'll just talk about lift. Well, you describe that lift in three dimensions. In X, Y, and Z. And if you, depending on how you define those at the center of gravity of the plane or the bird, you'll have a zero, and some value. You can have a unit vector where that value is 1. And the lift then is straight away from the Earth relative to the bird or the plane. Well, when you roll over, say, to the left, now that vector is you have a component of that vector, the 0, 0, 1, that is in the direction that you rolled, and that will push the bird or the plane in that direction. So if you're ever flying in an airplane, you notice that when an airplane turns, and there's more that's going on there than just, I don't want to get into too much detail, but you'll notice if you're sitting in an airplane and the pilot wants to make a turn, he banks over to one side, and that's why. So the Wright brothers observed that in birds and observed that the bird, in order to do that, actually twists its wings.
Yeah, not like a rudder.
Yeah, or an aileron, or and it acts like an aileron in an airplane. An aileron.
So it's like
it's almost.
And then it gives it this directed push towards the left when it banks like that. Yeah.
Yes, exactly.
Maybe that's the way to
Now,
think of a vector, like a directed push.
yes, yeah,
So like scalar versus
so
vector. A scalar might be $5, but
yes,
a vector would be a push in a certain direction.
yeah, exactly. It can be a vector. Lots of things can be a vector. Um, they tend to be drawn as arrows. When you're dealing with them. So that's one of the ways that the Wright brothers were very first-handed, very reality-oriented. Another one was after their successful 1903 flight, they went back to a place called Huffman Prairie, which is now Wright-Patterson Air Force Base in Dayton, where they lived. And they started to get really frustrated because they're trying to do longer range flights. And in 1904, they were just having terrible luck. They were not getting the amount of lift that they were calculating they should get from their airplane designs.
Mm-hmm.
And they were using lift and also drag tables that had been made up by Otto Lilienthal some years earlier. Everybody used these tables.
Yeah.
Everybody used them. The Wright
world
brothers
authority.
And the Wright brothers said, maybe we should double check the tables and see if they're right. And so they built a wind tunnel. Now, a wind tunnel, they didn't invent it.
Yeah.
They built a wind tunnel, and they started putting various shapes of wings in the tunnel and measuring the lift and the drag that they were actually getting and comparing it to what the table said. And what they discovered is that the tables had a value for basically the density of air that was 40% too large. And so lift and drag are linear functions for the most part of air density. So because that value was too large, everybody was undersizing their wings by 40%.
Oh, wow.
And when they corrected that problem, in 1905, they had enormous success. By the end of 1905, they had flown a distance of up to 25 miles, just doing laps around Huffman Prairie.
Cool.
And let me give you a third example of how they were nature-oriented, reality-oriented versus people. So, the opinions of other people. There was a point where they were just outside of Washington, D.C. I think this might have been Fort Myer. I'm not sure about that, but it was in 1908 or 9, I think. The entire United States Senate had adjourned to watch them to drive out there and watch a flight demonstration that the Wright brothers were going to do. The Wright brothers walked out of the hangar, checked the weather, didn't like the weather. It was not what they would want to fly in, and they canceled the flight.
Cool. As opposed to the Challenger, which they launched anyway.
Yes, exactly. And the newspapers were just shocked. How dare they do this? The Senate was present and blah, blah, blah. They're like, no. This might have been after, I believe it was Orville. One of them actually had an accident that he never really fully recovered from in 1908. And they promised their parents, for example, that the two of them would never fly in the same airplane at the same time. Because they didn't want their parents to lose both of their sons in one airplane crash. Which gets another thing, example of good versus bad engineering. I'll get into bad engineering now.
Is this other than the Wright brothers?
This is other than the Wright brothers.
Yeah, it's
This
like
is
one thing
actually
first. Let me
recent.
see. So, like, to kind of summarize, the first example you gave was about a bad analogy. People thought a boat and a plane were similar, um, and
Yeah,
clearly they had not
yeah,
thought through that enough to see about the dynamic characteristics, the drag, the propulsion, how one thing's on the water and others in the air, and how that works. Is it actually the same? And so, yeah, it's good the Wright brothers looked at a bird to see what they actually do to
yeah.
get, as you say, first-handed knowledge and see if the analogy is correct. Um,
Exactly,
and
exactly.
then,
It
and then, yeah, on the other one, you got that authority that they, I'm sure, appreciated. They didn't denigrate it, but they wanted to check it independently. Is this correct?
yes,
And so
yes,
we all have to think independently, even if that's one thing we should do in general. We should think independently about something and not just have group cohesion based on some idea someone believes and just all run with it. We should all be good and know what to do. That allows us to act better and then clearly to succeed. You got this group following some authority. He's wrong. Oh, but he's the world's greatest, so he must be right. Well, no. So the Wright brothers did their
yes.
experiments in the wind tunnel to verify. And I think they actually found they needed different numbers too. I think they found some of the stuff that was thought to be relevant actually wasn't, and they used other parameters instead to figure out how to fly and how to turn.
I don't recall that,
Yeah.
but essentially, when you know that's the essence of it. They didn't just bow to authority. You know, they said, okay, the authority says these are what the values are. These are what the tables are. But using those tables, we're not getting the right results. So let's verify the tables.
Mm-hmm.
And you know, Lilienthal was in his own right a brilliant man, but everybody's capable of error.
Yeah, even what was it, Maxwell, who miscalculated the age of the sun and the age of the earth?
I don't know.
Or no, Rutherford. Rutherford. That's it. Remember him thinking that they didn't know about nuclear power, didn't consider it, and so, based on thermodynamic considerations, he famously miscalculated the age of the sun and the age of the earth.
Okay.
Or Galileo, he didn't know about electrical forces, so he thought things were held together by vacuum cohesion, you know?
Sure.
Instead of saying, I don't know, he kind of jumped to that conclusion. But anyway, you want to like give another example and about time to wrap up, and we can develop more of this later. But we got what engineering is. We're getting some examples of good and bad. So good content, good start. What else do you want to add?
So another example, well, I gave some thought to, well, what makes bad engineering? And I've seen examples of that over my life. One of the things that makes for bad engineering is what I would refer to as the failure to account for failure.
Mm-hmm.
So if you or the listeners remember the whole issue with the Boeing 737 MAX?
Nope. Don't recall.
Okay. It's a version of the Boeing 747 that has been grounded by the FAA for over a year. And it had a design feature in it that would automatically pitch the nose of the airplane down if it detected an imminent stall. So what's a stall? Stall basically means you can vary the lift on a wing by basically changing its angle, what's called the angle of attack relative to the airflow. The higher that is, the more lift you get. Up to a point. If you go too high, usually around 20 to 25 degrees relative to the airflow, the air separates from the top of the wing, and you get a sudden drop in lift. And what pilots are trained to do, I did a little private flying lessons once, and I hated doing this, is the right thing to, because flight instructors, they're notorious. They'll tell you to do something you know is wrong. They'll say, okay, we'll practice stalls. We'll go back on the yoke until you feel the bottom drop out. I'm like, I don't want to do that, but you have to, but in the right way to recover from a stall is to basically push the yoke or the stick forward and go nose down. You'll lose some altitude, but you'll regain your lift. And so this has been, at least in piloting and aerospace circles, a big issue over the last year to two. So, and always when you see some kind of a failure, very often it's are you still here?
Yeah. Hello.
Okay, so somebody else tried to call me. I think it's a junk call.
Okay.
And if it's not a junk call, anyway. So the problem with the 737 MAX actually originates to the 1960s, even though it was the cause. It was cause of a couple airliner crashes. One in, I think, Egypt or Ethiopia, and another one in Indonesia. But the problem started in the 1960s. And it has to do with, in the 1960s, that's when the first 737s came out. The engines were simple turbojet engines. And then later on, I think starting maybe in the 70s and 80s, they started coming out with what's called a turbofan engine. And a turbofan is, if you look at any modern airliner, the engines are kind of cylindrical, but then they have a larger cylindrical section in the front of it. That's what's called the fan section. And basically it's a glorified propeller. It's not burning fuel to generate thrust, but it's augmenting the thrust that comes out of the back of the engine. And the bottom line is it makes the engine more fuel efficient, but fatter. So the Airbus A320s and A321s, which were designed in the 1980s, had taller landing gear than the 737s. And so some years ago, one of the engine manufacturers came out with an engine that had about 15% better fuel efficiency. So if you're running an airline, that's a big deal. And you want those engines. But the problem is if Boeing wants to put them on the 737, it's too big, it's too wide. And it could, on takeoff, it could actually collide with the runway and scrape along the runway. And Boeing decided not to put longer landing gear on the 737s. What they did is they raised the engine up relative to the wing, where the top of the engine cowl was actually in front of a little bit in front of the wing itself. So this creates a more pitch up kind of characteristic and makes the plane more prone to potentially stalling. And so they said, we're going to put in software to, if it detects a certain angle of attack value, to automatically pitch nose down. Now, where my spider sense would have been going off in these meetings is there's all kinds of things that we do, and satellites and all kinds of devices that we have that are automatic safety features. The first question that somebody should have asked is, okay, if this automated response gets kicked in, started due to a false alarm, due to bad sensor data, is the system just as safe as it was, safer, or less safe? In this case, it would be less safe. And even though the 737 has two angle of attack sensors on it, they decided to use only one of them. And so if you've got something that goes wrong in that sensor that's telling the flight computer erroneously that, hey, I've got too much pitch, you've got another sensor there. You should be bouncing against each other and telling the flight crew something's wrong, and they didn't. And, basically this caused two airline accidents. Hundreds of people died.
Wow.
And it's only over the fact that nobody thought to think, well, what if this simple little device fails? And they found out later that the two angle of attack sensors were differed with each other by 20 degrees, which is enough to be the difference between a stall and not a stall. Mm-hmm. It's just that the one that was too high was the one that the computer was reacting to. So I'll give you another example really quickly.
And that one was
failure
so that's basically bad engineering, not having good systems in play, just like you see Apollo 13, or you read about some of the stuff that was done for some of the rocket launches, and they would try to consider everything, right? What could go wrong?
Yes.
And so if Boeing had done that, then this probably never would have happened.
Yes.
If they had more of a system like that, or like there's in Japan or something, they got the 5 Ys, WHYS, not necessarily 5, could be 30, could be 3, but you don't leave the table until you've reached a root cause and you've considered everything, kind of like similar kind of system that should be in play.
Mm-hmm. A similar thing. It's like if you've seen the movie Apollo 13 and the explosion happens and all these consoles
recommended.
Yeah, it's my favorite movie. And there is a scene where Gene Kranz asks a guy named Cy Liebergo, who's got the console, so is this instrumentation? And it can't be instrumentation. This is 4 failures deep. By asking that question, is this instrumentation? It'll give you an example. If you're driving along in your car and your fuel light comes on, does that mean you're low on gas? Or is there a short circuit that's turning the fuel light on falsely? Mm-hmm. And so the way you should handle that is like, okay, look at the fuel light and the gas gauge. If the gas gauge is almost full, but the fuel light is on, probably have a bad fuel light. Mm-hmm. And this goes all the way back to John Glenn's flight. If you remember, they had to cut his mission short. NASA was going to have him fly 7 revolutions around the Earth, and he only flew 3. And he re-entered with the retro pack still attached to the heat shield. And the reason for that is they got a light coming on that indicated that his heat shield was loose. And the way that worked is basically they had 3 switches at 120 degrees apart on the base of that heat shield. And they work very simple devices. They work like the switch on your refrigerator that tells it to turn the light on when you open the door. Mm-hmm. They found out there was a heated argument about what they should do and who was in charge, actually. And when they recovered the capsule, they found out there was nothing wrong with that heat shield. It's just one of those little switches that popped open. That's an example of instrumentation. So one of the things that when I was in NASA in Houston, when we first met, was looking at a design, and you see a sensor, and we were all, the design engineers hated us because they'd say, "Hey, look, here's how this system we've designed is going to work," and we're looking at it saying, "Yeah, that's fine, but I want to know how it's going to break." Because I'm going to be sitting there having to deal with the malfunction. And so, we would constantly be saying, "Oh, look, you've got some kind of temperature sensor here or there. Could you put a second one in there?" So if we get right next to it, and before we wrap up, I guess one more quick example of not accounting for failure is, and this is human failure, is something that happened a few years ago, very close to where my parents live, probably about a quarter of a mile away, half a mile or so. What happened is it was an Amtrak train derailment. A train derailed on a bridge over Interstate 5 outside of a town called DuPont, Washington, on the southern tip of Puget Sound. And some people were killed, and the train derailed and fell off of a bridge onto the freeway.
Wow.
This was the very first passenger flight, or for lack of a better word, but this is the very first time that this particular rail route had carried passengers. And what was at issue was Amtrak decided that they wanted to build a express track that goes from Tacoma south on its way to, because the way it was before, you lost several hours if you wanted to go from, say, Tacoma to Portland, because you had to go through this circuitous route into Tacoma and around Tacoma. And so they put in this express track. What happened was they tested it in broad daylight under good visibility conditions, and everything seemed to work fine. But this morning, it was before sunrise. This happened in late November, early December, and so it was dark. And as is probably happened in the Pacific Northwest, it was raining, and you had bad visibility. So you had a very straight section of track, but then to get across the interstate, you had a sharp left turn over the bridge. And the speed limit for the bridge was, I don't remember the exact numbers, either 30 or 35 miles an hour. But the train would normally travel along at 60 miles an hour. 1 mile before that bridge, there was a single sign that says slow down to 30 or 35, whatever that number was. One sign. And nobody thought to ask, well, what happens if the train operator misses seeing that sign?
Because he reaches down to get coffee or something, right? Well, yeah.
Yes, exactly. He reaches down for his coffee, and he misses this tiny little sign, by the way.
Wow.
And which is what happened. And now he's moving along at 60 miles an hour. He's got 1 minute to figure out that left turn is coming up. But he's never run on this particular track before.
Wow.
So, if this had been a more seasoned train operator who's done this run a number of different times, he might have figured out without the sign. And the solution could have been as simple as putting at least one or maybe two more signs along the track.
Or lights.
Hey, 2 miles. Or something.
More lighted.
2 miles before you got to slow down. 1 mile before you got to slow down. Slow down. Right. And so now the operator has to miss 3 signs in a row, which is much less likely to happen. And something as simple as that. It's like when they put in this section of track, nobody sat down and asked, it's like, well, okay, we got a sign here that tells the operator what to do, but what if the operator makes a mistake, like anybody can? Like the Otto Lilienthal did, right? So.
Wow. Interesting but sad.
So.
But cool. And we can dig into some more examples in the future.
Sure.
Some other stuff, but yeah, good initial discussion of what engineering is, some of the thinking involved, good and bad engineering, how that's based on thought processes. So cool. Any last words, Hannes, before we wrap up for today?
No, I need to head over to a friend's place to pick something up.
Okay. So we better just cut. Cool.
Okay.
Awesome. Appreciate the discussion. Thanks a lot. So hope you have a good day and a good week.
And you too.
Thank you. Talk to you later.